people in presence, so we're still waiting, so we will wait just 5 minutes just in case. And I want just to be sure that Azim Wanous is here. Okay, thank you very much. And Elena Nicora. Elena? Okay, so we will switch to the first one only. And so. Se si connettono dalla regia, mi dite qualcosa? Okay, change of plan. So we have a switch. So I'll ask Azim Wanous to, sorry for the pronunciation, to come to the stage and start his presentation. He was here. Azim? Oh, come on. He disappeared right now when we need him. He was here 2 minutes ago. In the meanwhile, I can tell you a joke. Elena Nicora, has she somehow appeared? Okay. For the people who is present for the first time to a conference, when there is your session, you should be present before the session begins, so that the chair doesn't have a hard time doing his job, unpaid for. And Elena Nicora, has she appeared somewhere? Is she here? Okay, thank you very much. Perfect. So we have 2 speakers. Well, we had 2 speakers. Now Azim, is he here? Okay, perfect. So I think we can start with the people present. Okay, so please come to the stage. Perfect. And then, unless the 2 remote presenters connect, we are going to show their pre-recorded video. Of course, it's uglier, and we would like to avoid the thing, if possible. But anyway, we will cope with that. So we will start with paper ID 103, and then we will move on to paper 132. So the first presenter is Azim Wanous. Please come to the stage. And sorry for the pronunciation of your name, if I got it really wrong. So try to start it. Let's see if everything works. Okay, let's see if it appears on the screen, just to be sure. Here we are presenting, so please, guys. Well, hello.
One moment, please.
Okay. Okay. Okay, I think we can start. So the floor is yours.
Thank you. Hello, everyone. I am Hazem from IMT Nord-Europe, University of Lille and Crystal Laboratory in Lille City in France. I'm going to present you our work, First Piano, a new egocentric hand action dataset oriented toward augmented reality applications. Hand action recognition from virtual and augmented reality present interesting and promising subject of research, which is until now underused and underexplored. With the emergence of the term metaverse, and we can see that a real need exists actually to develop systems or light algorithm, but efficient one, which can be done, run in real time on limited resources on these kind of devices. Then our objective is to deal with this kind of devices in this context and these limitations. And as applications, we choose the instrument musical, especially here the piano. Learning a musical instrument, it's a task, hard task, which take several years of learning practices. It's already good to have a teacher or monitor, but sometimes in a COVID pandemic, it's good to have tools which can help the learner in the process and provide assessment of the playing, recognizing, but also propose feedback to the learner. And then to construct or to start with, several things were taken into consideration. The first one, it's the scale construction. Scale construction, if we speak here about scale in the Western musical instrument languages composed of 7 scales: do, re, mi, fa, sol. And the objective here to construct basically on this type of scales. 2 things to take into consideration for scale construction: the keyboard layout, which is composed of keys, white and black keys. Here we can distinguish two type of interval. Tone interval, which is the interval between 2 keys, 2 white keys separated by a black one. And semitone or demitone, which is interval between 2 white keys without being separated. Here I just give you 2 examples of C major, do major and re major, who is composed of sequence of alteration of tone, tone, demitone, tone, tone, and etc. The second thing important also for this kind of practices is also the player gestures. The player gestures, especially the order of finger when playing with piano. For example, here when you play with right hand, there if you see here the right hand order finger, we started by the finger 1, 2, 3, then we repeat 1, 2, 3, then 4, 5, and we return 4, 3, 2, 1, etc. The same thing is concerning the left hand order. This is something important which to take into consideration. Now about the acquisition, we use it for the acquisition of data. HoloLens device proposed by Microsoft, version edition 1. This device is composed of several type of sensors. The first, we have RGB sensors, but the problem with this sensor, it's the field of view, it's small. Then we opted a small, it's a small field of view, not permitted to have the hands when playing normally. Otherwise, we won't depend the head in order to take into consideration to capture the hands, but it's not practice. Then we opted to the use of 4 peripheral grid-level sensors. As you can see here, the 4, in addition to a central depth sensors, which have wider field of view. We choose to consider only 7 measure scale, the 7 scale do re mi, and for each one to label these scales, we opted for a labelization composite of 5 digits. Each digits can be 0 or 1. For each one of 7 scales, it will be a single right or wrong played, 0 or 1. And if it's 0, then it's an error. If it is error, it can be a wrong gestures, a wrong notes played, forget note, or also something like explicit note. This error can be accumulated. Then if you exclude some classes, we can go up to 19 different classes. Now about the data structures. Our data structure composite are the following. We have 7 major scales here. Each one have 2 folders, rightly player and wrongly player. 2 folders for each one, 12 trials, and each one has played 4 cases. The first one, right hand crescendo, going. The second one, right hand crescendo, then decrescendo, go and return. And the same for left hand. In total, we have about 700 sequences, video sequences, recordings, with all information about the annotation and the subject and all different things. Now going about the benchmark, which we proposed here. We proposed here the first benchmark to test our this benchmark on these data sets. We proposed our approach published recently in ICPR 2 years ago, about 2D deep video capsule network with temporal shift. Our approach is composed of 2 modules. The first one about the capsule network, the second is about the temporal shift. The capsule network proposed initially by Jeffrey Hinton's teams in 2017, where the idea is to critical issue of the pooling operation, but also advantages of this kind of about this architecture. It's that it proposes an architecture less deeper than a 2D CNN with the same or similar accuracy. Second things, it takes into consideration a relationship between features. It's based on 2D, CNN features, but put into a relationship between features of CNN. Like this, for example, we can characterize face by, for example, 2 eyes with symmetrical position, with orientation, with something like this. As, for example, for CNN, the output is scalar. Here, the output is vectors. Backpropagation, not used here in this architecture, but here, a dynamic routing algorithm is proposed. The second part of this, of our method is about the video consideration, the temporal shift here. The temporal shift based on the idea is to not using architecture which require a hard or heavy structure like 3D CNN or 3D capsule network, but to shift the information being still in 2D. Here, the idea is to shift the information from layer to layer. As here, each capsule composed of features issued from CNN. We take features, some part of features from previous and feature frames and share this information, replace it in the next capsule layers. It can be done in offline and online. The difference between the two, in offline manner, we can share between previous feature in the actual, but in online, only on we share the previous. To test its efficiencies, we test several kinds of shift temporal manner. The first is to shift the first kernel of first capsules. Here, the idea is taken from the original paper presented by Lin and et al. In 2019, where we proposed it to do it on the 2D CNN. Here, it's naive representation of this, but on capsule networks. The second one, we share the information. We shift the first kernels on every capsule. As you see here, each part here, a capsule, we share for each one the information between frames in the time. That's the last one. We shift of every kernels of every capsules. Here, we share the information more. Here, can you see it? That we share all these informations of every kernels on first capsules. The old architecture of our work can be resumed here as shift conf caps. It's very similar to those proposed by capsule layers. The only difference here that we do the shift between, this is the output of CNN. We shift here on the CNN, but also we add a residual branch, which can be combine the original with the shifted one. Like this, we prevent the loss of information coming from the shift CNN. And we group it on the capsule layer groups like it here, and we can concatenate it in the final architecture as deeper as you want to have a bigger or deeper architecture. Here you can see the architecture for classification, but you can add also a deconvolution layer, which can be as a decoder. For experiment, we have two types of experimentation for us, binary classification and multi-class classification. For the multi-binary classification, to classify as good or not, rightly played or not. For the multi-class classification, we classify each one of the scale, but also its wrong, independently which type of wrong played. We done it for several source of data, especially you see here for the green level, we juxtaposing it as panorama, we give it to our architecture. We compare the results with different type of convolution and temporal shifting. The best one is obtained for when we shift every convolution on first capsules. Same results it's obtained here by just using depth streams, but the results can be seen here for example, for multi-class classification can be degraded because the problem become harder and maybe the data is not big enough. As a conclusion, we proposed here a method related to the hand action recognition for first-person scenario, especially for piano playing application. Data are recorded directly from the augmented reality hand-built sensors. First benchmark has been evaluated on the piano data sets with preliminary results, but interesting. In future, it can be interesting to add new recording for measure scale, new exercises at the situation of the hands, more written, different written. For the final objective, it's to develop augmented reality human-assisted musical instrument tutoring interface. Thank you for your attention.
Thank you very much. Okay, so is there any quick question? Because we're running a little late. Just for the records, are you planning on using the audio also in the data set, or is just video only? And just why, in case?
Yeah, you are right. We have the audio, but we don't use it in this work. It's interesting, I think, to combine it later for in the interface. But in this work, we only use, because as you can see, we have just applied an approach already done for video.
Perfect. Thank you very much again. So thank the speaker again.
Thank you.
And so, okay. Credo che abbiamo abbiamo gli stranieri, sì. So, do we have the remote speakers connected? Yes, so let's see who's connected. Okay, so we have the second paper, so we are again on schedule. And can you hear me, Dominique Rufenack?
Yes, I can hear you. Can you hear me?
Perfect. So I think we are ready to start. So I asked yes, we can see your presentation. And please, the floor is yours. You have 15 minutes.
Thank you very much. Welcome, everyone, from Switzerland. And the talk today is going to be about keyframe insights into real-time video tagging of compressed ultra-high definition content. I'm Dominic, and I'm with Mobius Labs, the Berlin-based startup working on computer vision. So let me start by introducing this end-to-end video tagging pipeline. So typically, we have compressed video content, and we want to add metadata. So we have, there's a flurry of deep learning techniques to train image or video tagging, right? That's in the box on the right. So in comes a set of frames which are at a fixed resolution, usually very low resolution. And then we have the CNN or transformer, which then outputs the list of tags. Now, the green part is usually ignored. I have not come across a work that actually considers the time it takes to decode the frames and prepare them. So that's what this work is about. Why does it matter? If we look at the end-to-end processing time, at full HD content, 85% of the time from an input video to getting the tags is actually spent just decoding the frames. Right? For 8K resolution, it's 99%. So I would argue if you want to speed up this process, if you gain a few milliseconds here in the tagging model, but you're not considering the time it takes to get the frames, it's actually quite an important aspect of it. So in order to understand why do we spend so much time getting the frames, let's have a very brief look at how compression works, right? So a video is quite simply a sequence of frames. And as we see here, I show a few frames extracted every 1 second from a video. And as you can see, there's 2 shots. Shots are kind of semantically similar frames. And this is what compression makes use of, because instead of sending or compressing each frame as an individual image, it only compresses a few so-called keyframes. You see them below as the red frames, and all the other frames are predicted from them, right? So as you can imagine, especially in the second shot, where not a lot is changing, if anything at all, instead of sending 3 individual frames, you just send what you could not predict, which has a much lower bitrate requirements. So that's how compression works. And the problem is, if we now want to randomly extract a frame, which is not necessarily a keyframe, it will take a lot of time because multiple other frames have to be decoded. So in this work, the main question is, do these keyframes actually form a good subset for tagging tasks, right? And we test this idea on the specific task of video genre tagging. So what is video genre tagging? I'm referring here to this excellent overview by Mangolin et al., where they looked at this task with multimodal models. Very interesting figure. The important part is we have a movie as input, and out comes a set of genre tags, such as an adventure movie, science fiction, drama, crime, and so on. And what they do is they explore multiple modalities, audio, video frames, which is basically what you get when you have the video. Then there's additional stuff like subtitles and movie synopsis. And they test over 60 different models and combinations. And interesting is that to benchmark this whole thing, they also provide a data set of 14,000 video trailers together with the genre tags, the ground truth genre tags coming from TMDB. So how do we go about this? It's very simple, really deceivingly simple. We take a compressed video, we extract all the keyframes from it, and each individual keyframe is passed through a genre tagging model, which I'll show on the next slide how we train it. And that produces a set of tags per frame, per keyframe. So with these per frame tags, we then pass them into a conditional pooling, which outputs a set of tags, which we call video level tags. The percentage up here is not a confidence, it's actually how often and how many keyframes does the specific tag, the specific genre tag appear. So as you can see, we're getting more information as just hard, yes, there is action, or no, there is not, but there's also quantification of it, which is an additional nice feature. And also important, in order for this to work well, we also have a filter which removes uninformative frames. So especially in trailers, there's a lot of just text, which is not really informative. And if we want to apply this on whole movies, we have to ignore those because they're not present in typical movies. All right, so how do we train this? Again, very simple. In the yellow box, you see the actual genre tagging model, which consists of a off-the-shelf EfficientNet V0 backbone. And then we have a fully connected layer on top with 19 units. These correspond to the 19 genres that are in the dataset. At training, we have access to more frames, right? Because we're only concerned using keyframes for speed. But during training, we can actually live with a bit longer, and we can pre-extract those frames. So we do this, we extract 3 frames per second. This can be seen kind of as a nice data augmentation strategy. And then we run a shot detector on these frames and select 1 frame from each shot per, per epoch. And then we just do normal training, multi-label training to train the weights of the model. That's it. Very simple method. I think the interesting part of this work lies in the results. So let's have a look at this in terms of speed and also in terms of quality. So frame decoding speeds. If we just look at the green box I showed on the initial slide, which is extracting the frames, right? This is irrespective of the downstream task. We have to extract the frames. How long does it take? So I show on the x-axis, you see different resolution input video. And on the y-axis, the speed measure is in x times real time, which means if I have, for example, a 10x real time performance, it means that on a 10-minute video, I take 1 minute to extract the frames. So higher is better. Now we see 3 bars. The red one is if we just decode all the frames of the video. The green one is if we decode only the keyframes, which is significantly faster, as you can see. But now one might argue, well, yes, if you only decode the keyframes, you're just decoding significantly fewer frames, right? Just as an information on the data set at hand, there's roughly 1 keyframe every 3 seconds, right? So I also show results in the orange plot for decoding at 0.3 frames per second, which comes down to extracting 1 frame every 3 seconds. So we roughly extract the same number of frames in the orange and green curve. Yet you can see that there's not a significant boost in speed compared to the red one, which is exactly due to the thing I mentioned in the beginning, that these frames are actually predicted from other frames. So in order to randomly access one, you have to decode a lot of frames, which are then thrown away. And it's very, very difficult to keep track of all these frames in an intelligent manner. So it's the only quick thing we can do is to actually only decode keyframes. And as you can see across resolutions, this is around 30 to 40 times faster than decoding all the frames. We look at the end-to-end speed, so now including the genre tagging time, which is fixed, right? So the data set, if we look at these statistics, the average duration of a trailer is around 2 minutes, and there's an average of 71 keyframes. And here you can see the average time it takes to decode the keyframes. And the average genre tagging time is the same across the resolutions, because as I mentioned initially, all these frames are reduced to a specific input rate to the model. So we're not benefiting from this high resolution in any way. And this is with all the modern models, right? They have a fixed input resolution. And as you can see, speed-wise, this end-to-end, we can tag genres at around 100 times real time for a full HD movie, which means a full Hollywood movie, 90 minutes, takes less than 1 minute to get the tags. Just to highlight, if we want to do the same thing for fixed frame rates, then at 8K resolution, it runs at 0.3 x real time. So very, very slow, not practical at all. Now, of course, the question is, yes, this runs fast, but how well does it work? So here I refer to the results of the best results of single modalities from each modality from Mangalin et al. As you can see in green, there's the frames. They extract 120 frames per trailer at a fixed window. And then they use a 3D convolutional neural network, which, as already mentioned in the previous talk, they're much more involved than 2D networks, 2D convolutional networks, which the proposed method uses. Yet we significantly outperform this. And also, if we look at the best performing method, they combine the frames and the synopsis, is slightly better than the proposed method. But I would argue that if you have access to a full synopsis of a movie, you probably already have the genre tags as well. So I question a bit the practicality of this. It's interesting to see that you can improve the results of synopsis, but yeah. Qualitative, and this is the last slide of this presentation. We have an example from a movie called Metallica Through the Never, which is tagged as a music movie. If you run this through our model, the detailed analysis shows, yes, there is a lot of music, but there's a lot of action contents. And if you go further down, you see that there's actually horror content, right? This particular frame is one of the reasons it contains horror, this blood hand. Definitely not something I would expect in a movie that says music. So with the detailed analysis, you get additional insights on the content. So to conclude, I think we can say that keyframes do form a representative subset to do video genre tagging. And the proposed method runs over 10 times faster than real time, even on 8K resolution content. And I would like to end to mention that it also has wider applications for all video analysis tasks that don't require a kind of a fixed frame rate as an input, such as is often used for action recognition. And below, you just see an example of a model we're currently using, which just does general image tagging. So input is just the keyframe on the left, and on the right, you see the tags that are added with the confidence of the model. So yeah, this concludes my talk. If there's any questions, I'm happy to answer them now, or shout me an email at dominic@mobiuslabs.nl.
Very much. So Let's see if there's any question from the audience. No questions? Okay. So just one curiosity. So you said that you're sampling at 3 frames per second for the training phase, or am I wrong?
That's correct. Yes.
Okay.
Correct for the training. Yeah.
So did you try different decodings? So I mean, decoding at 3 frames per second requires you to decode everything anyway. But if you just pick P frames and you exploit the structure of the compressed video, maybe you can have without having such an heavy full decoding, you can get all the frames. So does that impact on the final?
Yes, very good question. So I totally see where you're coming from. Why is it 3 and not 6 for all the frames? The reason is mainly a practical one. If you decode all the frames, you have to store them somewhere, right? They're dumped onto some storage, and it's just we find in practice at 3 frames per second, so 1 frame every 300 milliseconds, is enough to, you know, if you go and extract all the frames, there's very little additional information, especially in the case of video genre tagging, right? You don't expect the video genre to tag faster than at a 300 millisecond rate. So for this purpose, I think this is more than enough. And I did not explore other frame rates, but just in our practical applications, we rarely use more than 3 frames per second for for video level tagging.
Thanks to the speaker again, and
thank you. Goodbye. Have a nice rest of the conference.
Thank you very much. So we can move to the next presenter, which is Elena Nicora. Okay, she will be presenting exploring the use of efficient projection kernels for motion saliency estimation. And okay, I think we are setting up. So we are missing the first presentation. So if you're interested in that, just wait, because we will be showing the video just after this presentation. The floor is yours, and you've got 15 minutes.
Thank you very much. Good afternoon, everyone. I'm Elena Nicora. I'm a postdoc at the Machine Learning Genoa Center at the University of Genoa, and I am here to present our work that investigates the potential of a family of efficient filters, the gray code kernels, for addressing visual saliency estimation. Motion perception is one of the first abilities that developed by our cognitive systems. In fact, since the earliest days of life, we are able to focus our attention on moving objects in order to understand what is happening around us without actually having to process all the visual stimuli that our eyes captured. And this is related to the notion of visual saliency that in the computer vision community is commonly associated with 2 concepts. The first is center surround differencing, that basically defines saliencies as the ability of something to stand out with respect to the surroundings. The other is more related to motion and is perceptual grouping that allows us to perceive elements that move together as a single entity. Of course, the immediacy of this biological immediacy of capturing, of focusing the attention on motion is not trivial to be implemented. An object is considered salient from a computational point of view if it has relevant motion and if it appears repeatedly in a sequence. More generally, this motion detection step is often part of more complex computer vision pipeline that involve the observation and the analysis of movements. And this detection step, for example, is defined as, in literature, as foreground segmentation for motion saliency detection or even video object segmentation. But the many shapes of these motion understanding tasks correspond to, of course, different computational methodologies that are very skilled for the task that they aim to, but they provide poor generalization ability when the task slightly changes. And we know that this diverges from the behavior of biological systems because we know that as humans are able to transfer information from one task to a related one. Additionally, in the recent years, deep learning solutions established a sort of monopoly, reaching outstanding results, especially in image and video processing. But the problem is that methods like this come with major drawbacks. In one concerns time and computational complexity. They also require a huge amount of data to train. And this might not be suitable for all the approachable tasks or all the field of application. So for example, in particular, when we have to deal with pipelines like the one that we saw in the previous slide, where we have various steps, and for example, the motion detection part needs to be computed real time. So the aim of our approach is to quickly identify the salient moving part of the scene in order to discard the irrelevant pixels and lighten up the computational burden. So in order to, in view of higher level tasks, for example. And we want to reach a trade-off between effectiveness and efficiency by leveraging the characteristics of the gray code kernels. The gray code kernels are a family of filters used in literature mainly as a fast 2D image filtering solution, and they have been applied to classical computer vision tasks such as pattern matching and the fast search of patch nearest neighbors. No. Their efficiency is discussed in Benarzi et al., where they show that under appropriate conditions, successive convolutions of an image with a set of such filters can be obtained using only 2 operations per pixel, regardless the size of the image, the size of the kernel for each filtering. And for example, as a comparison, in order to obtain the same exact result using a classic 2D convolution with a kernel of dimension k by k, we will need k to the power of 2 operations per pixel. So using the gray code kernels, we are able to go for an exponential complexity to a constant one. For this reason, we wanted to extend the available theoretical formulation for 1D and 2D to a 3rd dimension. So adding introducing the temporal axis on these kernels allowed us to obtain 3D filters in order able to highlight in a very simple way spatial, temporal, and spatiotemporal changes of the input. Considering our interest in motion information, we focused our analysis on temporal and spatiotemporal filters, and we designed a pipeline that is able to, that by highlighting the oscillations in these filter responses, is able to gather motion cues from RGB videos. The pipeline is composed by 2 modules. The first one starts from the application of a bank of 3D gray code kernels to overlapping clips of video, ending with a clip representation formed by a single 2D projection for each kernel belonging to the family. The obtained representation is then compactly represented by means of pooling, and ending with a clip description composed by 2 different maps. The first one is obtained computing the max pooling over the spatiotemporal projections. The second one computing the average pooling over the temporal projections. And as one can see from the examples, from the max pooling, we are able to gather a visual impression of where the motion occurred in a time span covered by the filtering that in our case is 4 consecutive frames. And obtaining a sort of 2D impression of the movement evolution. And with the average pooling, instead, we gather cues on how the motion evolves in time, obtaining two distinct blobs of values in correspondence to the last position of the moving object, that is the yellow blob, and one in correspondence to the past position, that is the blue shadows. These maps are given in input to the attention module that will combine the information in order to obtain a refined segmentation of the moving object. And a first coarse segmentation is obtained by thresholding the max pooling, and successively the information of present and past are exploited to refine and consolidate the final map. To test the potential of Gray-Coat kernels projection, we targeted video object segmentation scenarios, and we evaluated our method's ability to localize and segment salient motion. For this reason, we decided to compare our method with classical motion detection approaches of similar complexity. In particular, we chose two different optical flow solutions and the one algorithm of background subtraction. And for this reason, we decided to discard, for example, state-of-the-art solutions based on deep learning solution, because the level of complexity of the approaches, the level of the results, and the final goal is at a different scale with respect to ours. So the results that we show here are from the SegTrack V2 dataset. We chose this dataset because it gave us the opportunity to reason on different scene conditions. In particular, we put an emphasis on the amount of camera motion that our method is able to tolerate, the camera motion that is inside the sequence. Overall, our approach has the best performance across the different scenarios with a higher stability, highlighted by the lowest standard deviation. On the negative side, with fixed cameras, the accuracy of our segmentations is not the best, but considering our main goal of quickly detecting the salient motion, we can see that if we have a look at the actual segmentation, we can see that they are very much in line with the ground truth. So in comparison to other approaches, our method is generally less influenced by camera movements and achieves best motion localization indicated by the overlap of our bounding boxes and ground truth bounding boxes on 2 out of the 3 camera settings. From a computational viewpoint, with the use of a filtering scheme with constant complexity, we managed to reach higher, on average, higher performances than the 2 optical flow algorithm, with an execution time that can be considered similar to the very simple background subtraction method. No? Sorry. So wrapping up, we proposed a novel method for motion saliency estimation based on the efficient computation of 3D Gray-Coat kernels, and in the experimental setup, we evaluated our method as a solution for video object segmentation, showing that we are able to effectively and efficiently identify the portion of the image where motion is occurring, with a little bit of tolerance on the variety of scene conditions. Since the submission of this work, within my PhD thesis, we extended the pipeline in 2 different directions. One is towards a much more competitive segmentation ability by adding a module that fuses together to the motion-based segmentation mask that I presented today, an appearance information, with the aim of tackling more specific segmentation problems where, for example, motion information alone is not enough to identify the moving subject. On the other side, we employed also the pooling representations as descriptors in an action recognition scenario, closing in in a sense, an entire motion understanding pipeline with the use of only one efficient feature computation. I think that's it, and thank you for the attention.
Thank you very much. Okay, any question? Please, we have a question here.
Thank you for the presentation. I had just a curiosity. So the algorithm works using a sequence of frames for detecting the saliency for an object, and then after using the sequence of frame, you're using a threshold for the last frame of the sequence, or the whole sequence of frame is used for the whole sequence of salient object segmentation. I don't know if, do you understand?
Yeah, I understand. Thank you. Thank you for the question. We compute the projections on overlapping clips, so throughout the whole video, and then the projections are crushed together, are pulled together, and I have a single representation for each clip. So basically, we have a single representation for a clip of 4 consecutive frames, and all the information are used.
Okay, thank you very much. Any other question? Just one thing, I didn't see, so you mentioned efficient, but I didn't see anything about efficiency in the presentation, but maybe I missed it. Okay?
Yeah, I know. I mentioned that we are able to acquire the same results. We have a computational time similar to background subtraction that is one of the simplest.
Perfect. Yes.
I did not put the actual number in the presentation because it would have not been a fair comparison, since we used, well, our algorithm, I coded the algorithm, so it might not be optimized at best, while for the background subtraction we used the OpenCV optimized algorithm, so maybe it's not really comparable, but we are in the same range of execution time.
Okay, thank you very much.
Thank you.
So thank the speaker again. And okay, now we have the last chance for the remote person, the remote presenter of the first paper to connect. Is he connected? No. So we're going to see the pre-recorded video, and well, I think we wait for the background to send it. No questions, please.
Hello everyone, my name is Ujjwal Tiwari and I am here to present cycle consistency-based method for learning disentangled representation for stochastic video prediction. The goal of video frame prediction is to build intelligent systems that are capable of predicting future frames of a video sequence from a given set of context frames. To accomplish this task, it is essential for these models to develop an intrinsic understanding of the laws that govern the physical world. Video frame prediction models have been studied in a variety of different contexts, such as activity prediction, early recognition, human pose estimation, and autonomous navigation. Video frame prediction methods face 2 significant challenges. Learning the nonlinear transformation between frames is computationally expensive and produces degraded long-range predictions. The task of video frame prediction is inherently multimodal due to the stochastic nature of video data, and modeling the predicted distribution of future frames is challenging in high-dimensional video pixel space. Concurrent research can be classified into significant paradigms of interest: unsupervised learning of disentangled representation from videos. These methods disentangle video representation into time-independent and time-dependent components, namely content and pose. These methods exploit the temporal structure and the latent generative factors of videos in a predictive autoencoder setting. Learning disentangled representation of video sequence significantly reduces the complexity of predicting future frames, which can then be modeled as predicting the low-dimensional pose-latent vector for each time step. In our method, we validate the efficacy in learning disentangled representations on both synthetic and real-world videos. The other important area of research is stochastic video prediction. In these methods, disentangle video representation into stochastic and deterministic components and use stochastic latent variables to model the ambiguous nature of future frames. For example, VAE-based methods like SVGLP, SV2P, and SVGFP produce diverse predictions, but the predicted frames are blurry. Methods with CAN formalism tend to produce sharper predictions, however, are susceptible to mode collapse and training instability. In this work, we build upon SAVP and SVGLP and disentangle the latent representation of videos in a self-supervised manner by employing a cycle consistency based loss to their learning objective, and also apply a minor architectural change by using a content encoder to factorize video representation into content and pose latent vectors. Our task is to predict the next T frames of a video sequence by conditioning on a subsequence of C frames. Formally, given context frames x1 to C, we need to predict future frames x, C plus 1 to C plus T. In our model, we assume that the video sequences are generated from an underlying directed graphical model in which each frame is generated from two disjoint latent variables representing content and pose. In our approach, a future frame is predicted by using pose and content latent factors by using a generator. The generator is conditioned on the time independent content information by using a recurrent content encoder. The recurrent content encoder produces encodings which are consistent across all context frames. We apply our novel cycle consistency loss term on two different VAE-based stochastic video prediction architectures. The inference module consists of two recurrent content encoders. The posterior model models the posterior distribution of the latent variables, whereas the prior encoder is used to learn the learned prior distribution, which is the conditional distribution of ZTP given Zx1 to T minus 1 of the pose latent variables. The pose latent variables are sampled from the posterior distribution during training and from the learned prior distribution at inference time. It is important to note that in case of our VAE-GAN based SAVP baseline, two learned discriminators are used to discriminate the ground truth samples from posterior generated frames and from prior generated frames respectively. The below figure shows the implementation of a cycle consistency loss term. In the left, we show the forward prediction of frames, and in the right, we show the reverse predictions of the frames. The forward and the reverse predicted frames are used to optimize the L2 based loss function, which we use to tune our model. We evaluate the competence of our approach in learning disentangled representation of videos and study its effect on long-range predictions on both synthetic and real-world video datasets. For BEAR, we quantitatively evaluate the fidelity of generated frames between SAVP and CC-SAVP by computing structural similarity and peak signal to noise ratio. We assess the perceptual quality of generated frames by computing the cosine similarity between VGG features. In this slide, we show the synthetic MNIST datasets qualitative results, where we compare CC SVGLP with SVGLP baseline Pose latent variables from the red bordered sequence are used to generate a new sequence along with content information from the frames in the green border. It can, it can be clearly seen that our model learns proper post-content disentanglement. Here, we repeat the experiment from the top image on CC-SVGLP with multiple contents from images in the green border. In the right section, it can be seen each row is a long-range prediction of 200 frames by CC-SVGLP given 5 context frames. And the predicted frames are much more crisp. Here we demonstrate post-content disentanglement on bare real-world video dataset by SAVP. The pose information of the predicted sequence from the top row in red are applied on frames in green with different content information to generate subsequent sequences. It can be seen that the model has accurately learned to disentangle video representation. Here, frames on the left are used to generate multiple long-range stochastic video predictions. It can be seen that the system generates varied, sharp predictions up to 150 time steps. Note that the generator has been conditioned on only 2 context frames. The above 3 plots depict the average similarity between ground truth frames and the best predicted frames. For each test sequence, we pick the best predicted sequence out of 100 predictions and average the similarity score over all test samples. VGG cosine similarity scores match better with human perception. It can be seen that our model CC-SAVP significantly outperforms SAVP on all 3 evaluation metrics. In conclusion, we experimentally demonstrate the efficacy of our model in learning post-content disentanglement on 2 different stochastic video prediction models by simply conditioning the generator with time-invariant context information using content encoder. In this work, we formulate an easy-to-interpret and train cycle consistency loss term, which helps learn a, a refined predictive model of the time-variant stochastic latent variable pose. Our evaluation results concretely establish the qualitative and quantitative advantages of using cycle consistency loss and our approach in learning factorized pose and content representation for long-range video prediction. By applying cycle consistency loss on 2 different stochastic video prediction models, we show that this approach is sufficiently general and can be incorporated in other similar latent variable-based stochastic video prediction models. Cycle consistency enables model to learn complex distributions of pose. Thank you very much.
Okay. Okay. Good. Okay. It's okay. Okay, welcome to the poster session 1. I want to ask to all the poster presenters to gather just below the stage. Meanwhile, I want to remind to the audience that they can join the presenters at the boxes at the first floor. So all the presenters have 2 minutes flat of pitch, so I recommend you to stay within the time. So let's start. The first poster is FrameNet, tabular image processing, pre-processing based on UNet and adaptive correction. Authors? Not here. So we have then course to find VQA by iterative conditional refinement.
Okay, let's go ahead. Then we have a contrastive distillation approach for incremental semantic segmentation in aerial images. No? You can join, anyhow, you can join the poster in virtual rooms on the WoW application. So then we have in-painting transformer for anomaly detection. No. DASP dual encoder for screen prediction. No. Cluster-based convolutional baseline for multi-camera vehicle re-identification. Fourier mask instance segmentation using Fourier mapping in implicit neural networks. Is it the correct session? Okay. Towards an efficient facial image compression with neural networks. Okay. So the presenter is, you can say your name.
Hi everyone, I'm Maria Ausilia and I'm from University of Catania. Today I talk about the facial image compression with neural networks. This is a significant topic in surveillance scenarios because the image compression does not compromise the facial recognition as the second step. For this goal, we develop a simplistic convolutional autoencoder that consists of 3 parts: encoder, binaries, and the encoder, and we can compress images of any size. Another novelty is the custom loss function that consists of 2 parts. One part that works on pixel space and another part that works on features space. We have made some experience and we achieved promising and valid results comparable to that of JPEG standards. Thank you for your attention.
Thank you. Then we have interactive deep annotation as DA or RAS, object detection supervision for efficient instance segmentation. Spatial UNet, deep learning-based lane detection uses fisheye cameras for autonomous driving. Exploring fusion strategies in deep multimodal affect prediction. Okay. Welcome. You have 2 minutes.
Hi everyone, I'm Raffaella Lanzarotti from the University of Milan. In this poster we present, and this paper, we present a study to evaluate the opportunity to adopt a multimodal method to inferring the emotion expressed by people. And we explore in particular the audio, video, and 2 physiological signals, specifically electrocardiogram and electrodermal activity. We combine them, we analyze first with CNN and with RNN deep networks, fusing them in 3 different ways. So specifically early model and late fusion, concluding that on this data set, the most promising feature is audio, and the couple of features is audio and video, but that also physiological signals help in this task, and that the most promising way for fusing this information is the late fusion. More details in the paper and poster. Thank you.
Thank you. Then we have graph-based generative phase anonymization with pose preservation. Okay. The floor is yours.
Hi, I'm Nicola Dallazeng from University of Pisa and University of Trento, and in our paper, Graph-Based Generative Face Anonymization with Post-Preservation, we proposed a novel GAN for face anonymization, which takes as input a source face to anonymize and a non-sensitive condition image. Our method is composed by two branches, one that takes as input the raw images, and the second one that takes as input the landmarks of the two faces and builds a bipartite graph between them, and then integrates the appearance information from the source and the condition in order to acquire the non-personal information from the source image, such as lighting, background, and skin tone, and the facial information from the condition. So the final generated image shall have the non-personal attributes of the source and the facial identity of the condition. To ensure so, we have the two discriminator, one for the pose and one for the appearance. And our test on two publicly available datasets show that we outperform state-of-the-art in terms of face naturalness and post-preservation, while being comparable in terms of face anonymization. Thank you.
Thank you. Then we have key landmarks detection on cleft lip, repair partially occluded facial images for aesthetic outcome assessment. Real-time hand gesture identification in thermal images. Learning advisor networks for noisy image classification. Yes, we have. Okay. Yeah.
Hi, I'm Simone Ricci from the University of Florence. I introduced my poster. Deep neural networks are prone to performance reduction when they are trained on dataset that contains a large amount of mislabeled data. And this is typically present in online collection of data for image classification. And we proposed an advisor network that helped the classifier to leverage all the information present in the training dataset in the challenging case of mislabeled samples. The advisor network is a fully connected model that automatically learns through a meta-learning strategy how to generate attention mask to be applied to the visual feature extracted from the classifier. The advisor network is utilized only during the training stage and will be discarded at test time. And our results prove that this method works even on artificial dataset and real dataset containing noisy annotation. So, thank you.
Thank you. Next is low light image enhancement using image to frequency filter learning. Then improving localization for semi-supervised object detection. Okay, here we have the author.
So our work was on semi-supervised object detection. It means that we are object detection, but in semi-supervised learning. So the majority of the images, we don't know anything about them. So we started from the state-of-the-art models called Unbiased Teacher, composed by a teacher and student. They are the same models, faster CNN, that are training simultaneously. And because 1/3 of the pseudo-labels generated by the teacher are completely wrong, we included a new branch on the models of the faster CNN to classify the bounding box IO quality, so that can be used in conjunction with the classification confidence score to better filter out the wrong pseudo-labels for training the student. And also we found a good way to include also the unsupervised regression losses, because usually the original model don't use them because they say that they decrease the performance. But that's because the errors in bounding box regression is multiplied by 3 to 5 times, because usually the component for the losses on the regression is bigger than the classification. So we found the good way to balance the loss between the classification and regression, and we were able to include and increase the final performance. So then we included both contribution, and we increases the performance of the general models. So thank you very much for listening.
Thank you. Then we have towards open zero-shot learning. Okay, we have the presenter.
Hello everyone, my name is Julio Davila. I'm part of the Italian Institute of Technology and the University of Genova, and I'm going to talk about towards open zero-shot learning, right? We are introducing this new framework that expands on generalized zero-shot learning, in the sense that in generalized zero-shot learning, you only have 2 types of classes, unseen and seen. The objective is to train a classifier to recognize instances that haven't been seen on training time, right? So you train with the seen, classified on the unseen, and we believe that this doesn't apply to the real world scenario. So we expanded to the open set by including a new type of class called unknown. Now in this framework, we have to now to be able to classify seen, unseen, and be able to identify and reject the unknown classes. We present this framework. We also present the metrics to evaluate its performance, and we also propose a new method called semantic-based unknown generation, or SBUG, in which by learning the semantic distribution of the class attributes, we can generate samples of the unseen, the unknown, and also the seen to train a classifier on these samples. Our result shows that we have obtained an improvement in the state of the art, and if you have any question, please join the virtual session, and I will gladly explain everything. Thank you.
Thank you. Exact affine histogram matching by cumulance transformation. Road quality classification. Yeah, we have the presenter.
Hello everyone, my name is Martin Lang. I'm from the Czech Technical University in Prague, and my paper is about road quality classification. My initial motivation was planning a journey on road bike or motorcycling using only high quality roads. So I wanted to build a machine learning model which would automatically do it for me. But I found out that there was no suitable dataset for my task, so I created our own. That is the main contribution of this paper. I collected over 7,000 images from Google Street View and manually annotated it into 6 classes and made some classifiers on it. So far, I was building classifiers using MobileNet version 1, MobileNet version 2, and the accuracy of the classification is about 75%, So there's a lot of room for improvement. However, it does this job, what it was designed for. As you can see on this little map, I'm able to make path segments based on the quality. So there's a visible trend of the quality of the road, and I'm able to use it for my initial task, for my motivation. It's a quite challenging task because the road has a lot of light variety in it. Sometimes it's pure shadows, sometimes it's very strong light from the sun rays, and therefore there's a lot of opportunities for pre-processing the data set and a lot of future work. Thank you. If you have any questions, I'm open.
Thank you. Then we have image novelty detection based on main shift and typical set size. Did you?
So, hello everybody. My name is Matthias Hermann from the University of Constance, and my main background is industrial inspection systems. And here in this work, we try to find a new way for detecting anomalies in images. There are basically a lot of approaches to do this, but during experimenting, we found that a small, simple baseline method was always similar in performance. So here we propose a new 5-step mean shift detection algorithm that is shallow, easy to implement, and fast in practice. And very interesting for searching hyperparameters, we could incorporate the typical set theory, which is well known in information theory and things. So yeah, you're invited to join me in the session.
Thank you. Then we have a deep learning-based system for product recognition in intelligent real retail environment. Okay.
So I'm Marina Polanti, assistant professor at the University of Macerata. I belong to Bright Vision Robotics and Artificial Intelligence Group, a group based on between two universities, University of Macerata, University of Ancona, and this work arises from an important collaboration with Grottini Lab, which is a company based in Porto Rican IT, leader in retail environment solution. In particular, in this paper, we proposed a deep learning pipeline for monitoring the status of the planogram, because it's really important to detect and automatically recognize the product on the shelf. In particular, we propose a deep learning approach able to recognize the single SKU on the shelf, but not only to detect the product. After that, we are able to recognize the product by the EAN, the European article number, and which is really important to effectively recognize the product. Then we collect a novel dataset specifically collected for this task, and this dataset is publicly available, so if you have any requests, please contact us, and for any details, you can read our paper or contact us. Thank you.
Thank you. Next is synthetic data of randomly piled similar objects for deep learning-based object detection.
Hi, hello, my name is Jan Sarens. I'm a researcher at Institute of Electronics and Computer Science, and this is the poster of the paper, synthetic data of randomly piled similar objects for deep learning-based object detection, and I will start with why. So real data is hard to label, it's time consuming, it's tedious, and a human error can arise. And we try to improve these things by synthetically generating the data. And in this case, this is randomly piled objects in the container that are overlapping each other, and they are similar. So we made the synthetic data generator framework in the Blender, and we explored how different kind of ratios of synthetic data and real data affects the object detector's performance. And in the end, actually, if we add synthetic data to real data, we got increase in the average precision until the 50-50 ratio, but in the end, the just poorly synthetic data performed less good than the real data. But with the synthetic data, we can generate different kind of corner cases that we could not even generate but get with the real data. And one aspect of this paper was also if we can detect at least one object in the scene with the intersection over union threshold over 95%. And we managed to do that in every scene when the models were trained on the synthetic data. So thank you.
Thank you. Then we have PolygloNet, multilingual approach for scene text recognition without language constraints.
Hi, my name is Alex Solé. I'm from Bicomtech. And basically, our approach was creating a new pipeline for syntax recognition. So in traditional pipelines, you have first the detection that extracts the bounding boxes. After language identification, that selects one of the set of the recognition models that you have. So in our approach, what we did is instead of having a language identificator, we do the inference using all the text recognition models, and we move the intelligence to the post-processing that we use some LCTM encoder decoder to process the text and select which is the correct sentence, and also has the ability to correct the correct detection based on the other languages.
Okay, thank you very much. The next is self-supervised prototype conditional few-shot object detection. Okay, move on. Real-time respiration monitoring of neonates from thermography images using deep learning.
Thank you. Hi, I'm Simon from Aachen, or Aquisgrana, how you Italian guys know the city, from Germany. And we are working on the camera-based wireless time measurements for preterm infants. So every year there are 15 million premature infants born worldwide, and 1 out of 10 of them die due to the complications related to preterm birth. One of the big problems is that the state-of-the-art monitoring is with cable-based sensors, with adhesives. And the problem is when you change these adhesive-based sensors, like ECG, like temperature measurement, sometimes the PPG sensor, then you can harm the patient because there is immature skin, and in the worst case, there is an infection. So there's an injury and an infection, in the worst case, a sepsis, which is one of the problems with the highest mortality rate. And therefore, we try to get rid of all the sensors with adhesives and measure the vital signs using cameras. So for example, RGB camera for PPGI, which is the heart rate, and very related infrared camera to measure the surface temperature. And what we did in this work, we used the YOLO V4 object detector to measure or to predict the head and the nostrils, to measure the fluctuations of temperature in the nose region, to then measure the respiration of the infants. And we did some pre-processing steps, then trained the object detector, and then we predicted the respiration and the respiration rate and compare that to our reference signal. So if you're interested in this work or in camera-based vital sign measurement for preterm infants, just join me. Thank you.
Thank you very much. The next is one-shot HDR imaging via stereo PFA cameras.
Hello everyone, I'm Fatima from Ca' Foscari University of Venice. And the paper that we have worked on is one-shot HDR imaging via stereo PFA cameras. So our title has two terms in it. One is HDR and the other one is stereo polarized cameras. So what is HDR? With the normal cameras, when you try to capture a scene in which we have like an object which is very high illuminated and the other objects are dark, then you see this kind of maybe underexposed images or overexposed images, because the cameras, they are not capable to capture a lot of illumination information from the scene. So to solve this problem, there is a technique called HDR, high dynamic range imaging, and most of us, we have it in our phone and we use it without even knowing it. And the other thing is stereo PFA cameras. These are new type of polarized cameras. They have sensor in it, and they allow us to capture simultaneously 4 different images of the scene with different polarizer in it. And as you can see in the second column, it looks like these 4 images are taken with different brightness or different exposure. So what we did is we proposed a new type of camera setup using these polarized cameras, and we did high dynamic range using these type of new cameras. And our contribution is we proposed a new type of camera setup, we proposed a new type of camera model, and finally we proposed a new data set, and the results, they look promising. And if you want to know about the details about our work, you can join my poster, or you can write to me, or you can read our paper. Thank you.
Thank you very much. The next is connected components labeling on bitonal images.
So, good afternoon, everybody. This is Federico Bolelli from the University of Modena and Reggio Emilia, and our paper is about connected components labeling on bitonal images. So, as you may know, connected components labeling aims at extracting objects within binary images, and state-of-the-art algorithmic solutions are based on 2 scans approach. So basically, during the first scan, the input binary image is analyzed in order to decide which label to assign to each pixel. So in order to do that, a scanning mask is used. The scanning mask defines the current pixel or block of pixels that have to be labeled, and the neighborhood that must be analyzed in order to decide which label assigned to the current block. During the second scan, the provisional labels are replaced with the final ones. In order to be used, the block-based mask requires the pixel inside the block to be connected based on the chosen connectivity. So our work focused on the optimization of the first scan. We define a systematic approach to use masks that may contain inside the block also not necessarily connected pixels, and this allows to enlarge the size of the mask, of the scanning mask, and improve performance. So if you are interested in how the algorithm works and on experimental results, please join the Zoom meeting at poster 202. Thank you.
Thank you. Then the next is panoptic segmentation in industrial environments using synthetic and real data.
Hi everyone, I'm Camillo Quattrocchi, PhD student at the University of Catania, and today I'm going to present my work, panoptic segmentation in industrial environments using synthetic and real data. The main contribution of my work is the generation of a synthetic data generation pipeline useful to generate synthetic data, useful to deal with the problem to acquire and label new real data, and useful to study the panoptic segmentation task. This synthetic pipeline is able to generate synthetic data and the corresponding segmentation mask, and also is able to generate segmentation masks starting from real data. Using this pipeline, we generate a new dataset that have an industrial laboratory as domain, and we use this dataset in order to conduct experiments and study in order to evaluate and demonstrate the efficiently of the use of synthetic data in order to reduce the gap between the real world and the virtual world. So we train the model of panoptic segmentation using 2 different settings. The first setting uses only real data, while the second setting uses both real and virtual data. Thanks for the attention. If you want to join my virtual session, you can meet me upstairs at the room 22. Thank you.
Thank you. The next one is egocentric human-object interaction detection exploiting synthetic data.
Okay. Hi everyone, I am Rosario Nardi, a PhD student at the University of Catania. Today I will present my work entitled Egocentric Human-Object Interaction Detection Exploiting Synthetic Data. So the main goal of this work is understand how humans interact with the world from a first-person perspective. This task is particularly interesting and challenging is particularly interesting due to several real-world applications. For example, if we have a model, a system that is able to detect interaction, the system is useful, can be useful to, for example, improve the safety of workers in a factory. However, in this domain, the industrial domain, this task is still understudied due to the limited availability of a public dataset. And for the expensive cost usually required to collect and annotate this kind of data, and also for privacy reasons. To this end, we propose a pipeline that is able to generate synthetic images of interactions and automatically labeled. And exploiting this pipeline, we generated a new photorealistic dataset of interaction of about 20,000 images. So to explore the usefulness of this synthetic dataset, we propose a method that is able to detect all the ends and objects, including both active and non-active objects, and determining which of these are involved in interaction. So if you are interested in or curious about this work, please come to join our poster session and visiting us on upstairs at room box 18. Thank you.
Perfect. So the next is weekly supervised attended object detection using gaze data as annotations.
Hi all, I'm Michele Mazzamuto, a first-year PhD student at University of Catania. So in our work, we consider the problem of detecting and recognizing the object observed by visitor in a cultural site from an egocentric point of view. So since labeling a large amount of data to train a standard object detector is expensive in terms of cost and time, we propose a weekly supervised approach to this task, which leans only on gaze data and a frame level label indicating the class of the attended object. So to study this kind of problem, we propose a new dataset that is acquired using a head-mounted Microsoft HoloLens 2 device, and that let us to acquire video and also gaze signal while the user were visiting a cultural site. So we explored 3 different weekly supervised approaches for the task of attended object detection on the collected dataset. Our experiment allows us to obtain satisfactory result in a weekly supervised manner. So the proposed approach allows us to obtain gain in time and also gain in reduced cost for the labeling of the dataset. Respect to a standard full supervised approach that is based, for example, on faster RCNN. So if you have any question, our poster session is the number 221, or you can meet me at the box number 19. Thanks for the attention.
Thank you. So the next is a deep learning-based framework for malaria diagnosis on a high variational dataset.
Good afternoon, everyone. I am Andrea Loddo from the University of Cagliari, and my poster is presenting a work oriented to a medical task, in particular the detection and further classification of malaria parasites and their life stages. In this work, we focused on a publicly available dataset acquired thanks to a collaboration with the Hospital of Lausanne. And as you can see from some images in this slide, the images presented very high variation. That means they have different illumination, brightness in general, coloration condition, and also some smear were very ruined due to the very much time inside the hospital. Moreover, this dataset is also heavily unbalanced on two sides. The first side is that we have a lot of images of Plasmodium falciparum, one of the 4 types of malaria parasites, and also inside of the Plasmodium falciparum images that are the main objects of this work, we have also an heavily unbalanced on the life stages. So we have more or less 1,200 images of the ring stage, and for example, only 7 images of the gametocytes stage. That means that in our work, we propose, first of all, a lot of augmentations in order to realize a good oversampling of the images and to train our method. In particular, our method is composed of 2 different phases. The first one is aimed to detect the parasite itself, and we propose a YOLO V5 object detector in order to make this detection in a near real time. Then the further classification step of the life stages of the parasites is performed thanks to Darknet 53 CNN. In particular, I want to emphasize the fact that Darknet 53 is also the backbone of the YOLO V5, even if in its cross-stage form. That means that it opened the field to further works where we can share the features between the detector and the classification stage. Long story short, the results of our method show that we are able to obtain a weighted F1 measure of about 96% in the classification phase, and
you have to go at the end.
Okay. So we outperform the state of the art, even though our method is open to improvements. Thank you for the attention.
Thank you. The next is first steps towards 3D pedestrian detection and tracking from single image.
Hello, I'm very glad to be here. My name is Gianluca Mancusi from the University of Modena and Reggio Emilia. Today I'm going to show you first steps towards 3D pedestrian detection tracking from single image. Well, until now, the problem of multiple people tracking has been solved using 2D data only. However, people move and interact in a 3-dimensional space. And for this reason, what inspired us is that moving into the 3D world will make it easier to distinguish people that are instead occluded in the 2-dimensional world. In general, what we have done is that we trained our method on a dataset that is synthetic, because there are no datasets that have 3D annotations of people or a good amount of annotation with 3D annotations of pedestrians in a crowded scenario. So, to solve this problem, we used ModSynth, a big dataset with synthetic data extracted from GTA, the video game. And so, our architecture, the 3D architecture, follows the idea of CenterNet. We predict 3D centers, widths and heights of people, but this time in a 3D volumetric space. And in a second step, we compress them because they are too big to predict directly, and also they are sparse. Well, in the end, our trackers works on this 3D space, and we noticed that in these settings, we have a reduction of identity switches, and so in general, an improvement of identity metrics. This is all, and if you want to know more, we can meet on Zoom. Thank you.
Thank you. The next is multivariate cumulative alignment for domain adaptation. Is that the mic?
Hello. My name is Mark. I'm coming from the Open University of Catalonia. And the work I'm presenting is on domain adaptation, which, for those of you who are not familiar with it, is based on training a data set on a model on a source data set, and then making sure that it will also work on a target data set for which we don't have labels for training. Usually you have some kind of domain shift that doesn't allow the model to work directly on that target data set. So there are two kinds of ways of solving this. We have a family of models which are non-parametric, that apply some kind of metric system to the latent representation of both domains and tries to minimize any discrepancies. And then we have parametric approaches, usually based on adding a new neural module, which models the distributions of both the source and target domain, and then some kind of adversarial training is used to minimize that discrepancy. The second ones, in general, obtain much higher accuracies due to them being able to model complex internal structures inside the probability distributions. What we present here is a model that is actually non-parametric, contrary to the mainstream, but still achieves results very similar to those, comparable to those of the parametric state of the art. To do so, we propose an algorithm that is executed in two steps, a metric. The first one learns a series of weights for the source samples in order to try to eliminate any kind of imbalance between the source and target domains. And then the second step uses a metric based on the cumulative distribution function of both the source and target distributions using random projections in order to avoid the problem of high dimensionalities of the space. That's it. If anyone has any questions or wants a more in-depth explanation, it's paper 25 of 9, and I'll be connecting right now.
Thank you. Then the next is self-supervised learning through colorization for microscopy images.
Good afternoon. I'm Nicolas Risciuglio from the University of Twente in the Netherlands, and I'm presenting the work of my master student, Vaidei Pandey, that could not be here. We addressed the problem of scarcity of labeled datasets, large labeled datasets for segmentation of electron microscopy images, and we did that by means of a self-supervised learning approach. We formalized a colorization pretext task and embedded it in the BIOL self-supervised learning architecture. With that, we trained two types of encoders, a ResNet-based encoder and a standalone self-attention encoder. And we found out that a combination of colorization and self-attention provides reasonably good models or pre-trained models for semantic segmentation of microscopy images. We are working on understanding the reasons behind that and how to further improve the models. So we would like to discuss that with you in the what remains of the poster session and later in the conference. So thank you very much.
Thank you. Then we have unsupervised anomaly localization using locally adaptive query-dependent scores. No. Then skew angle detection and correction in text images using RGB gradient. No. 6D OF pose regression via differentiable rendering. Go ahead. Mixing zero-shot learning learning unseen classes for mixed features. You are, okay.
Hello again. Okay, so we tackled the problem of reducing the bias in zero-shot learning. Given that the objective in zero-shot learning is to classify instances that haven't seen during training time, while training only on certain type of classes known as sync classes. This creates a bias towards these classes, right? Currently, the state-of-the-art base their approaches on generative models that learns how to create synthetic samples of the unseen sample of the sync classes to create, in this way, samples to train the classifier on, right? In any case, this procedure still has the problem for the bias. Even though it's reduced, it still exists. So we present a new way to train these methods by generating new samples, by creating a mix of the already existing unseen. And in this way, by mixing samples, we can allow the model to learn from a new distribution, which we believe this distribution shares similarities with the one of the unseen classes. In this way, after training the model, you can obtain a better performance and reduce the bias. We explore two approaches to mix these kind of features. One is mix-up and the other one is cut-mix. We applied these two types of techniques, and we discovered that it allows us to increase the performance of these methods. And if you want to check my poster, you can join the virtual session, and I will discuss any questions that you may have regarding this. Thank you.
Thank you very much. I think this is it, right? Because it's not going on. Okay. So you can either join the presenter at the boxes at the first floor or virtually using the web app, or you can get a very fast coffee break, since at 4 we have the invited talk. Thank you very much. The session is over.